First talk will be by Mendel Rosenblum, who will tell us what VMs are really about.
Thank you. So, so the first, I was actually asked to give a talk at a Usenix conference, which used to be a Java virtual machine conference. They dropped the J from it to just expand it to virtual machines, and they invited me as for diversity, I guess, reasons. I worked on something called virtual machines that appeared to have almost nothing to do with what the conference used to be about. And so I took it as a point to try to figure out what all these things that are called virtual machines have in common. So talk about what a virtual machine is and the differences. And then, since I've been working on this lower level stuff, and a lot of people have either never learned or didn't forgotten about it, I was going to talk about that a little bit of what we've been doing. A company that I was involved with. I should go back. I'm a professor at Stanford University, so I don't need a disclaimer about like that, since everybody knows professors don't
Can you speak for John Hennessy?
Yes. I'm also a co-founder and scientist of VMware, so I have to say that I'm wearing my Stanford hat today. Okay, so before you even start to think about what a virtual machine is, it's interesting to know what a real machine is. And I think there's a lot of agreement here. There's some layer of usually hardware, and this is like something you would need like a soldering iron to change. It's not a malleable thing that you have. On top of it, typically you put layers of software like an operating system and maybe application programs. So, this is a view of it. And so we have an agreement now. Well, in the 1960s, if you had said a virtual machine, there would also have been a lot of agreement. This was something that IBM invented. It was basically a layer of software that runs right on the real machine. And what this layer did was export and abstraction of a virtual machine. And that virtual machine had the same abstraction that the hardware did. And by doing that, you had this interesting property. You could take any software that was actually written for that hardware and run it in a virtual machine. And so, effectively, you look at this picture, there's a layer of software here exporting these virtual machines. So you have these virtual CPUs and hardware and stuff. And then you can run whatever operating system environment you did on it. And so this was actually a really popular thing. IBM did it. A lot of other companies tried to copy it. It looked like a good idea. In fact, when IBM had their mainframes, they were really expensive boxes. It made great sense to be able to carve it up and export lots of virtual images of it, particularly when there weren't a lot around. And there were entire conferences and a whole, research area of their virtual machines. But by the 1980s, when I was in grad school and stuff, basically, it looked like one of these ideas. That was funny when computers weighed 3 tons and stuff like that. But nowadays there's no use for it. Hardware got pretty cheap, so there wasn't. What do you need to have just buy another machine? You don't need that. And the other problem is, if you look at sort of modern, like PCs and stuff in the 80s, they were fairly wimpy, and you probably wouldn't be able to support a virtual machine hardware on it. This other thing happened that inspired IBM to effectively kill their virtual machine thing, and that was they got themselves in this fortunate position where they had 2 competing system software strategies. One of which was, we'll take VM and run a lot of single-user operating systems on it and build a multi-user system that way. The other way was a more OS-intensive. We'll write a multi-user, multitasking operating system and run on it. And they made a conscious decision to actually kill off this idea. I like comparing it to, like, rather than building something like Windows NT, you ran n copies of DOS at the same time on it. And it just, they made probably the right decision. And fortunately, it ended up, VM disappeared, and everybody assumed it was because it was a dumb idea. Even though there, as I'll point out, there were a lot of benefits that were interesting today. Well, in the 1990s, we saw a rebirth of virtual machines, but these were different sort of virtual machines. Well, these were abstract virtual machines. They were they didn't match the real hardware. They had some kind. specification of it. So example of that Pascal P system, Smalltalk, Java, Microsoft runtime, kind of language runtime. And so, typically these things, since they weren't effectively, trying to model all the hardware, you could just run them within the process of a modern operating system. So, here an example of the software stack as hardware, or the operating system software, and then within our process you have a virtual machine environment, a virtual machine environment on top of it. So, this, by the time when I started VMware in 1989, it wasn't clear that we could even call these things VM, even though, that's what they really were, since if you look back at literature, except that, everybody would look at us and say, oh, you must be doing Java stuff or something like that, since the term had been so co-opted by Java. I'll call this like a high-level language VM or something like that to distinguish it. So then it turns out that these virtual machines, they became a lot of hype around it. They basically, unlike the old virtual machines, you didn't have this existing software to run it. One of the nice things about matching the hardware is you take all the software written for it. There was no software for this. But you could say, look, if you target this high-level virtual machine, you have a better execution environment. You faster development time, you can write it once and run it anywhere. You get memory and type safety. Basically, all goodness and sort of what is managed, MREs, whatever it is. The world would be better if all code ran in these things. And, even the 2000, they're getting their own conferences and workshops all about Java VMs. But those aren't the only VMs. There are actually other types. And in fact, one way you can view this thing is that you have these layers of software. At any point, you can go and just slice a level through there and effectively get a VM. So for example, you could squeeze a layer between an operating system and the applications in it. And it's particularly easy to do on something like Linux or Unix, where that interface is relatively simple, as opposed to Windows with 80,000 system calls or something like that, where it's very complicated to do. So basically you can do that, and now you have each of these other applications. So people have done this, and to the point you can have applications that move between, that checkpoint themselves, or move between different environments, or sandbox for security. There's a lot of reasons people do this. That's one. Yeah, there are other ways you can slice to it. Like, for example, some people decide, why don't we take this modern operating system and just sort of draw a line somewhere through it? And we'll call those the sort of abstractions of virtual machines. And sometimes they say, well, if we draw it at a low level, it's sort of like hardware virtualization, but not totally there. They call it para-virtualization. And so that's also a common approach that people are using this day. Today, basically to take an operating system and try to make it so it'll run in some kind of virtual machine like containers, and take advantage of it. People have tried other ways. If you look at HPUX, when you do logical partitioning, or other ways people would do things, you could just find some point in your operating system to carve things. For example, at the hardware abstraction level, and then build containers, or whatever you want to call it. Yes?
So some of the examples, in particular this one, don't really virtualize the processor itself, or at least the instruction set of the processor. You're executing the same instruction set on the hardware, whereas previous ones like the high-level language VMs and some examples of a VM that's above the operating system also changed the instruction set. So you had to do a translation to generate code.
I guess so. I kind of view that as, you can have a virtual machine that enables direct execution, which is basically the trick that virtual machine monitors do. Or you can have one that requires an interpreter or a translator to run it. And that, to me, is a small difference in these things. But yeah, that. You can't, like things that one of the reasons people do para-virtualization is they're trying to make it so, like they're running an x86 now, so they can actually use direct execution. They change the semantics of it.
I'm not sure I got a small difference, but I agree with you that it's one, that there's maybe the way I would put it is there's two orthogonal things. One is abstracting the instruction set, and that's critical for things like JVM and high-level language virtual machines. And that's orthogonal to, in some sense, abstracting the resources in the underlying system, like disk and CPU and things that are managed typically by an operating system, which is what VMM seem to do, and which is what perhaps is.
Well, I guess it's from an implementer point of view, whether I run this code directly on the CPU or run it on an interpreter that interprets something or run it on a translator that's jitting it is, at least in my mind, not a, it's all running in the CPU. It's whether you have this another layer of sort of goo in there.
Yeah, I mean, I'll add to that in the sense that